Hey, let's talk about tree-based signatures again. This time a little bit more of a meta level. So how did we get here and what's happening? And then I want to talk about an alternative constructions of how to get from this tree-based idea to stateless signatures. So how did we get here? We started with a one-time signature scheme that was Lampard's, and then we extended it for allowing arbitrarily long messages. We did this using hashed unsigned. And from that, we constructed these tree-based signatures. My first question to you is basically good check of whether you understood all of this. Why couldn't we have just done the tree-based construction just using Lambert's signature scheme without hashed unsigned? So why is that? Well, if you think about this tree-based construction, remember that we had like public keys down here. So let's start with 2. And then in order to authenticate these public keys, we had another public key. And under this public key, we signed these 2 public keys. And then this one was again authenticated by another public key. Etc. So this is this tree-based construction. So now if we were to use Lambert's signatures, these public keys are supposed to sign messages of length n. So for Lambert's scheme, this would mean that the public key consists of n images of the one-way function. If these 2 public keys both have n one-way function images, and we want to use this public key to sign these 2 public keys, then this public key up here needs to be long enough to do this. So even if these one-way functions images were only 1 bit, which they can't be because functions that output just 1 bit are not one-way, but even then we would need a public key of length 2n. So 2n one-way function images. Okay? And then these 2 are both of length 2n by the same argument. The same holds for this node. So then this one would have to have length 4n. And you can see where this is going. So essentially, the fact that Lampard signatures have a public key that is longer than the messages it can sign, this is a big problem, because then like going through this tree on every level, essentially the size of the public key needs to at least double. And so if we have n levels and we get to the root node, then this root node would have to have length at least 2 to the n. And of course, this is way too much. We can't generate this many. So that's why we use this hashed unsigned thing in order to make sure that our public keys could always just have n one-way function images. And with that, we could sign as many bits as we wanted. Okay, but now if we think about this, we started with a signature scheme that was this hashed unsigned signature scheme. And essentially, we were able to sign messages that were as long as we wanted them to be. But somehow along this way of coming up with these tree-based signatures, we lost this ability of signing arbitrarily long messages. Now the message space, also the length of messages we can sign with tree-based signatures, is n. My question to you is, where does this requirement come from? Why is it n? Yeah, so the height of the tree is the thing that is n. So if I sign a message, I start at the root node. Then if my first bit is a 0, I go down to the left. My next bit is a 1, I go down to the right, etc. And then I essentially, for every bit that is in my message, I go down 1 level. So if I want to sign an n-bit message, my tree needs to have n-bit height. Another way to view this is here at the bottom, we have all of the leaf nodes, and each leaf node is exactly there for 1 message. So if we have n-bit messages, we need to have 2 to the n leaf nodes. So how do you fix this? How, if we now have the signature scheme for messages of length n, this tree-based signature scheme, how can we kind of adapt it to make it again be able to sign messages of arbitrary length? Yes, this is exactly right. This should be a first reflex for arbitrary length messages. In any case, use collision resistant hashing. So just take some hash function with the digest length of n, and then just do hash then sign for this signature scheme. So if we do that, we would essentially hash the message, and then we would go down this path depending on the bits of the hash. And through this generic hash then sign theorem that we had, that this is secure, we just get security from this construction. What I want to talk with you about is an alternative way of fixing this. So if we have this tree construction, how can we still get signatures for arbitrary length messages from this tree construction without just doing hash then sign? One thing we can notice is if we instantiate this whole tree construction with Lampert signature, with Lampert signatures, with hash then sign, then all of the public keys here at the leaf nodes, they're already able to sign arbitrarily long messages. We just choose not to. So, for example, this public key here, it's destined to sign 1011. It will never sign any other message. But it's a hash then sign scheme, so it could easily sign any other message, even ones that are really long. So let's say as a first step, we want a stateful signature scheme using this tree-based construction idea that can sign arbitrarily long messages. Do you have any idea how to accomplish this? This is kind of, I don't know whether this is an idea you can just easily get, but I guess my hint would be to actually use the fact that these signatures down here, they can already sign arbitrarily long messages. And you can use the state to make sure that after this node has signed a message, that it will never sign any other message. Okay, so the thing is, we have 2 to the n public keys. Like conceptually, we have 2 to the n public keys down here, and we are choosing which public key to use depending on the message. But let's just not do this anymore. Let's just go through them one by one from left to right and sign the ith message with the ith leaf node. So the first message that we get, let's call it M1, we just sign it with this node. To the signature, we would of course also add like these whole signatures and public keys that belong to this as before, but instead of signing 0000, we will just sign M1 here in the downmost layer. And then the next message, we could just use the signature key. And so on. And in the state, we will just keep a counter. Plus maybe the whole other state stuff that came with the tree-based construction before we got rid of the state. So this is definitely possible, right? And the proof is basically the same, I'd say. So why didn't we do this? Well, the kind of unfortunate part is that this counter here in the state, it's kind of harder to make stateless. Okay, so we were able to get rid of this tree state by observing that these public keys, secret keys, and signatures, we could just replace with randomness, and we can compress randomness very well with PRFs. But this counter, this is like a real state, right? So it's something we can't just emulate with randomness. Except that we can. So now that we have this stateful tree-based construction scheme that has all of the tree state and this counter stuff, how can we get rid of the counter? So my 2 hints for this is, 1, is it actually necessary that we go through these leaf nodes one by one? And 2, it would be pretty beneficial for us if we had like a randomized solution for this. So yeah, I guess my second hint kind of gave it away a lot. We won't sign messages one after the other, just going through the leaf nodes one by one. Instead, we will just choose a random leaf whenever we sign a message and just use that leaf to sign that message. And then because we have 2 to the n leaves and we choose a random leaf each time, we can kind of upper bound the probability that we get the same leaf twice. If we get the same leaf twice, then we've signed potentially two different messages with that signature. And then, well, we're done. We can't. Because it's just a one-time signature scheme and we can't just sign two messages with it. But because there are 2 to the n leaves, chances of finding a collision after polynomial many queries is low, very low. If we get a message M1, we just choose a random leaf and use that node to sign it. And then, of course, do the whole tree stuff as well, and so on. So through this randomness, which, by the way, randomness is always like a good candidate to get rid of state. Sometimes, instead of just remembering stuff, if there are enough choices, you can just choose randomly instead of remembering which ones you have already taken. So this counter is basically now gone. We don't have a counter in the state anymore, we just choose positions randomly. And now the only thing that's left is this tree state that we have in the state, but we already know how to get rid of this. And then the security proof of this is all very similar to the tree-based signature scheme. I won't do it here. It's just, yeah, the kind of the one bad event that you need to condition on is this collision event, that 2 different messages, so 2 different signature queries, were randomly mapped to the same leaf node. But yeah, you can upper bound this. For example, you can upper bound it using this birthday paradox theorem that we will see next week, I think. Which will tell us, like, if we do random choices for stuff, how many random choices do we need until we collide with something. All right, so these are the 2 ways to get from tree-based signatures to signatures of arbitrary length. Either just use hashed and sign, which is also like the easiest proof and stuff, or you can alternatively go with the road of choosing random leaves and signing the message with that. And I guess what I want to get most across is like this trick that if I have a counter that's only there to make sure that I don't have like collisions in like a huge sea of possible values, then I can just replace it with randomness and I will still be fine. Thanks for listening. See you.